Hello, in this video we're going to be talking about some sequences of real numbers and their properties. They can be talking about infinite sequences of real numbers, and they're going to have the following form. So, if someone asked you to list the squares of all natural numbers, you must begin by writing 1, 4, 9, 16, 25 and 36 and some numbers, yes? But you will soon realize that it's actually impossible to list all these numbers, since there are an infinite number of them. However, we can respect this collection of numbers in several different ways. Firstly, what is sequences? A function which is defined in sets of natural numbers is called what? Yes, sequences. Firstly, however, we don't usually use a functional notation to describe sequences. Instead, we denote the first term by A1 and the second term by A2, and so on. So for the above list, A1 equals to 1, A2 4, A3 is 9, A4 what? Yes, 16, A5 25, A6 equals to 36, and an equals to n squared. Yes, here A1 is the first term, A2 is second term, yes, and A3 is third term, and some number n is an nth term or the general term. Since it's just a matter of notation, we can use another letter instead of the letter A. For example, we can also use Bn or Cn or Dn, etc. as a name for the general term of sequences. A sequence. By the sets of natural numbers, we mean all positive integer and denote this set by infinity. An, yes, in the bracket equals to 1, open bracket, 1, 4, 9, 16, some numbers, and n squared, and some numbers. Sometimes we can also use a shorthand way to write the sequences. It's like in the bracket an equals to, in the bracket n squared plus 4n plus 1, means the sequence an with general term an equals to n squared plus 4n plus 1. Do you get it? Okay. An expression like A2.6 is nonsense. Why? Because, yes, 2.6 is nonsense. We can talk about 2.6 term of a sequence. Remember that a sequence is a function which is defined in the sets of natural numbers, and 2.6 is not a natural number. Clearly, expression like A0 or A-1 are also meaningless. Do you get it? Okay. We say that such terms are undefined. Okay. Next. So let's look at the examples. Yes. Okay, let's continue. Now let's look at some examples of sequences. Write the first 5 terms of the sequences with general term an equals to 1 over n. Here is a1 equals to 1, yes, and a2 equals to what? 1 over 2, a3 equals to 1 over 3, a4 equals to 1 over 4, a5 equals to 1 over 5. Yes? Do you get it? Yes, you get it. Next example. Given the sequences with general term an equals to 4n, yes, 4n minus 5 over 2n, and find a5, a minus 2, and a 100. We just have to recalculate the formula an, choosing instead of the nth numbers 5, minus 2, and 100. So a5 equals to 3 over 2, yes. A100 equals to 395 over 200. And we do simplify, and it gives us 79 over 40. And a2 minus 2 is undefined. Yes? Because minus 2 is not natural number. Okay, look at our questions then about these sequences. The sequence were xn equals to n. Is the sequence convergent? No. This is a divergent. Sequences, we just mean it doesn't converge because we don't allow infinite limit when we talk about convergent, of course. The sequences is heading off towards plus infinity, but that doesn't counter the convergent sequences of real numbers. It's a yes, it's not convergent. No, this is what? Divergent. So it's a sequence bounded again for essentially the same reason. It hits off to the right with no bound on it, so it's not bounded. Yes, it's not bounded, it's unbounded. Finally, it's a sequence xn monotone. That means all of the terms go in the same direction. In this case, it's a strictly increasing sequence. Each term is strictly greater than the term before, so the answer is yes. It's a strictly increasing sequence. It's a strictly increasing sequence. Okay, let's show to the fourth example. Yes, here is right. For each positive integer n, set xn equals to minus 1 to the n. The time sequence doesn't do very much, it just oscillates backwards and forwards between minus 1 and 1, with the first term being minus 1. So if I was to show you what the sequence did on the number line, yes, this is number line. I'll just be going back with them forwards between minus 1, yes, and 1. But it's certainly not convergent, so it's a sequence converging. No, xn is divergent. Even though it doesn't head off to either infinity It's still divergent. Second, is the sequence bounded? Yes, it's bounded because again the modulus of xn is always less than equal to 1. Yes, for all 1. For all n. Third question, is the sequence monotone? No, because the terms get bigger and smaller, bigger and smaller, then smaller, and the sequence oscillates. And I will write here, no, the sequence oscillates. Here I want to say definition. If a sequence contains a countable number of terms, then we say it is finite sequence. Second is, if a sequence contains infinitely many terms, then we say it's infinite sequences. It's like that. Here is fifth example. State whether the following sequences are finite or infinite. First is the sequence of all odd numbers. Yes, infinite sequences like that. You will do positive, yes, positive numbers goes to 1, 2, 3, 4, 5, 6, 7, and the plus infinity. If you do good things and you will do one good thing and you say, oh my god, it's perfect, I will want to do it again. And you will do infinity good things and you will develop and you have be good habits. Okay. Example, the sequence of all odd numbers, 1, 3, 5, 7, and like that some odd numbers. Since there are infinitely many numbers, here the sequence is infinite. Second is B. The an in the brackets equals to -10, -5, 0, 5, 10, 15, and some numbers 150. The sequence has a finite number of terms since the last term is 150 is given. So this is are finite. Third is 1, 1, 2, 3, 5, 8. This is finite or infinite. The sequence is infinite as some numbers, yes. Notation shows that there are infinitely many numbers. This is infinite. Okay, we have looked at a few examples of sequences, and in conclusion, I'd like to say that the more examples of sequences you look at home, and the more examples of their properties you examine, the better you're going to understand the concepts of these properties. Thank you for your attention. Goodbye.